Hello, everyone, and thank you so much for joining us. This is Georgie Carter from Palladium. I am delighted to welcome you to today's webinar entitled Predictive Analytics, Advances and Applications of Machine Learning in Global Health Programming. We have a great discussion lined up for you today, and we'll begin with just a few announcements. So this session is being recorded, and we'll be posting the recording to Palladium's YouTube page. We would love to hear from you, and we welcome your questions at any time. Please submit your questions on the chat box on the right side of your screen, and our moderator will read them aloud when we have time for questions at the end. Now, these web conferencing platforms are getting a high volume of traffic these days, so we do ask that you bear with us in case there are any glitches with the technology. And finally, we ask that if you are not speaking, please mute yourself to keep the line nice and quiet while others are talking. So that concludes our announcements portion, and it is my pleasure to hand it over to Tara Nutley, the Vice President for Data Informatics and Analytical Solutions at Palladium. Tara?
Great, thank you, Georgie. So hello, everybody, and welcome to this webinar. Along with Georgie, I welcome you all to this very exciting topic. As Georgie mentioned, I am a Vice President here at Palladium, and I lead a division called Data Informatics and Analytical Solutions, where we think about and implement a lot of this kind of work. So, you know, we've all heard about the potential of predictive analytics as a powerful tool to transform the performance of healthcare delivery in the communities and in the different countries and the different contexts where we serve. However, examples of implementation and resulting improvements in health outcomes in the development sector are scarce, and you know, I think we're all aware of that as well. But why is this? And it's really because it's taken a combination of three mutually reinforcing trends to come together to make predictive analytics more feasible and more powerful than ever before. And so first is the proliferation of data. So as many of you out there listening are aware, the volume of data in the global health space is growing exponentially. So from routine health metrics, electronic medical records, geospatial data, text data, social media, satellite imagery, etc. All of these data sources are contributing to this proliferation of data. Second is the growth in computing power. So it's not just raw computing power, but distributed computing and specialized processors that are really driving growth capacity. Third is the improvement in algorithms. Researchers are constantly making advances in algorithmic approaches to identify patterns, predict outcomes, model unstructured text, image, audio data, etc. And any one of these developments on its own would really be of only limited value. But together, the potential of predictive analytics for us in our work has really become a reality. So here at Palladium, we've applied our decades of experience in analytical and digital solutions, as well as our on-the-ground systems knowledge, to bring improved outcomes to the communities we're working in. We've leveraged learning. There's a lot out there, you know, building on USAID reports, such as making AI work for international development, other resources, and of course, the learning that many of you on this call today have generated. So it's these experiences that really have allowed us at Palladium to leapfrog progress toward global development goals. And so it's really exciting for us to be here today to talk about it, to share these experiences, and the following presentation will demonstrate just this, how Palladium is using predictive analytics to address practical analytic objectives. So that said, let's get into the presentations. First, we'll hear from Lorena Mate, whose team under the Kenya HMIS2 project, which is a countrywide project in Kenya to roll out electronic medical records. So how this project is using supervised machine learning to predict patient-level HIV test results, and is deploying the model via a web application hosted in Kenya's National Data Warehouse. So for this project in supervised machine learning, there's a particular outcome that we're trying to identify, and that's anomalous anomalous data points and routine HIV data as part of the Data for Implementation project. So that's presentation 1. And then the second is in unsupervised machine learning, there's not an outcome to predict. Rather, the objective is to identify patterns or segmentations that elucidate data. So then we'll hear from Lillian Magetto, whose Tupime County project is using time series modeling to evaluate the impact of the reintroduction of malarial spraying in 2 counties in the Lake Victoria region in Kenya. And each approach is different, right? And it's tailored to the respective project's objectives. Each is being used now to improve health outcomes and answer critical analytic questions, and is available to deal with immediate challenges at the country level. Okay, so that's a quick summary of our presentations. And now I'll turn it over to Laureen, our data warehouse analyst for the Kenya Health Management Information Systems Project. So Maureen, to you.
Thank you, Tara. My name is Laureen. I'll be presenting predicting client HIV test outcomes. So the Kenya HMIS project is funded by CDC and has developed information systems to ingest the client records from more than 1,000 health facilities across Kenya that provide HIV and AIDS services. The project has created a national data warehouse that stores client records centrally and has created a variety of analytic tools embedded in the warehouse. These help the government of Kenya to monitor progress towards epidemic control. Next slide. Next slide. To help reach the 95 targets, Kenya invests in HIV testing services to increase the share of people living with HIV who know their HIV status. However, the resources for testing services, including the provision of test kits and staff, is facing increasing pressure. Therefore, it's essential that the government allocates testing resources using analytic insights to increase the testing yields. The data set that we looked at, 1.9 million HIV test records, 73,800 were HIV positive. That is approximately 4% positivity rate. If the Kenya government could better target clients and location with testing resources, we could find more HIV positive clients while conducting fewer tests. To generate these insights, the Kenya HMIS project used supervised machine learning deployed on the national warehouse through the web application, which was developed using R programming language to predict client level positivity, considering factors or answering the 3 main questions like who are we testing, where should we test, and when to test. Next slide. So in the current workflow at the facility applies eligibility screening questions. So if we have the scenario that we have 20 clients come to a facility, from the eligibility screening questions, 12 are marked as eligible and 8 are marked as not eligible. This includes 1 client who's positive, HIV positive, marked in red. So out of the 12 that are eligible, 2 turn positive or they have a positive outcome, and that is a 16% positivity rate. But at the warehouse, as we said, the positivity rate is closer to 4%. Next slide. So as inputs to the machine learning process, we relied heavily on the national data warehouse. That is the client demographic data, testing data, and GIS data. We also added data sets for social economic and HIV metrics. These were collected 3 kilometers around the facility. This was to build a profile around each facility. Next slide. So to train the model, using Homa Bay County as an example, we began with approximately 44,000 client records, and this was split evenly by gender, and most of the records were between clans between 15 and 45 years of age. So we split the data set into three. That is 60% was used to train the model. That is the process in which the machine learning models learn the patterns associated with input data and the positivity. Then we use the next 20% to evaluate the models. And then the last 20% we used it to test only the best performing model. We trained models using logistic regression, random forest, XGBoost, artificial neural networks, and then we evaluated them, the performance using area under the precision recall curve. This is because it focuses on how well the model predicts our outcome, and in our case, the outcome is positive HIV tests. So precision, also known as positive predictive value, is a share of all positive predictions that were in fact positive. So if we make 100 positive predictions and 30 of them turn HIV positive, then our precision is 0.3. And recall or sensitivity is the share of all clients that the model correctly predicted would be positive. So if we have in our data set, we have 50 positives, and then we flag 30 as positive, that means our recall is 30 divided by 50, which is 0.6. Next slide. So the best performing model was XGBoost classifier, which achieved 0.54 positivity rate. So this was really good because considering the Homa Bay County at the warehouse, positivity rate is 0.05. So getting a 0.54 was really encouraging from the model that we got. So using the same county, if we have the 20% test data set is a total of 8,800 clients. So if, for example, we have constraints in Homa Bay and we are told we are the only 4,400 test kits available, so we need to test the clients. If we look at the graph, it sorts patients from the highest to the lowest probability of testing positive. So at the x-axis, we can only test half of the population. So we move all the way to 50 on the x-axis, meaning that is half our population because we only have test kits that can test only half the population. If we look at recall, which is red, we're able to identify close to 95% of the total positives in the entire data set. So meaning we have only tested half of the population, but we have gotten 96% of the positives. So meaning the other 5%, 4% is only on the other 50% that is remaining. So that is still a good outcome, getting 95% of the total positives. So again, if there is constraints again, and we are told now we are only able to test a quarter of the population. So on the x-axis, we move to 25. Then we look at the recall, which is roughly at 85%. So we are testing a quarter of the population and we are getting 85% of the total positives. And then for me, that was really good because we are able to do a trade-off. We don't have enough test kits, but we want to test this number of people. So we want to get more positives. So we can be able to use this model to help us. So when we get more test kits, more resources are available, then we can test all the clients. But depending on the constraints that we have, we can just decide on the population that we want to test, and we're able to see the number of positives that we're going to get from that. So yes, the next slide, please. So using the previous scenario, the ML model that we have, we are going to use it to assess every client that comes to the facility. So using the same example, the model predicted 10 people to be, assessed 10 people to be eligible for testing and 10 not to be eligible. It increased the positivity because we got 3 clients who are positive, and that is a positivity rate of 30% above from 16% that we had before. So the good thing about this is we have targeted testing, and it's helping a lot. Next slide. So practically, the ML app generates risk categories. So far, we have 4 risk categories. That is the low risk, medium risk, high risk, and highest risk. So these are defined by precision. So those that are flagged as highest risk, 75% of them turn positive. For high risk, approximately 50% will turn positive. And for medium risk, approximately 25% will turn positive. Next slide. So at the facility level, healthcare workers are able to access the ML model using the web application. That is the interface on the left-hand side. So all the variables that are there are shown. We are already collecting them. That is age, gender, marital status, and we know the facility that we are testing the client at. So then you generate the prediction, and you're able to get instantaneous results at the front end. So you're able to make a decision. So for our case, the client was flagged as high risk, and that is 50% of these people were flagged, clients were flagged as high risk, turned positive. So using the ML model, we're able to support targeted testing for clients and increasing their positivity. We're also able to support a distribution of test kits, I think, as we have seen before. So that is also a good point. So the last point is the clients who are flagged as medium risk, high risk, highest risk. We're able to target them for more counseling or preventative interventions like PrEP. But that is a value add that needs more discussions and stakeholder engagements just to decide how we're going to handle that. But thank you so much for the presentation. And I would like to welcome Yoni Friedman, Senior Technical Advisor for Data Science. Thank you.
Great. Thank you very much, Laureen, and good morning, good afternoon, everyone. Under Data for Implementation, or DataFi, a 5-year data and analytics project funded by PEPFAR and implemented by USAID, we leverage routine HIV data collected across PEPFAR countries, together with non-traditional data sources such as commercial, geospatial, and unstructured data sets to improve population and patient health outcomes. We use supervised machine learning using approaches similar to what Laureen just described. In countries such as Kenya, with large data warehouses and hundreds of thousands or even millions of patient records, work to predict and understand patient-level outcomes is growing. In these countries, and even more so in countries without such large data warehouses, routine HIV data is of critical importance. Routine HIV data, including facility-level metrics on testing, care, and treatment, disaggregated by sex and age, are a bedrock for monitoring progress towards epidemic control. Accordingly, USAID invests in capacity building and data quality assessments to secure high-quality data. These efforts to curate routine HIV data are valuable, but can be time-intensive and difficult to scale. They tend to rely on business rules and thresholds, such as defining acceptable ranges or ratios between indicators. These work well in general, but have the limitation that they will flag only those data points that clearly violate a rule. Sometimes issues with data reporting may not violate a rule or may be evident only when looking at the data from a multi-dimensional lens. By DataFi, we are developing an R-based tool that uses algorithmic approaches to identify anomalous data points in routine HIV data as likely data quality or performance issues, requiring root cause analysis. The tool will enable USAID to accelerate, automate, and standardize key aspects of data reviews. One approach we're using is called recommender systems. As the name suggests, this family of algorithms is used by companies to recommend products, think Amazon, or movies, think Netflix, that a customer might like based on his or her purchase or viewing history and based on common characteristics across products and movies. In fact, important innovation in the development of recommender system models was spurred by Netflix itself through the Netflix Prize, an open competition with a $1 million prize to the team that, using recommender systems, could best improve movie recommendations. This took place about 15 years ago and was one of the first $1 million data science competitions of its kind. Implicitly and sometimes explicitly, these algorithms identify types of customers or viewers, categories of similar products or movies, and learns patterns that describe what type of users like what types of products or movies. For example, someone in your household may like documentaries on predictive analytics. Other smaller members may like animated films about superheroes. Beyond product and movie recommendations, these approaches are used to identify fraud in the insurance industry and to identify suspicious tax returns for audit by the US Internal Revenue Service, the domestic tax collection agency. Under DataFi, we are using the approach to identify anomalies in routine HIV data. We swap health facilities in place of customers and HIV indicators in place of products or movies. We then run the similar algorithms to identify patterns between the facilities and the metrics, such as covariances or relationships between HIV indicators. As HIV testing metrics increase, what's the pattern associated with changes in care and treatment? We define these patterns a number of ways. Looking at all facilities together, we separate patterns for males and females, the idea being that metrics reported may appear strange compared to general patterns, but when compared only to metrics reported for females, they appear more normal. We also look at patterns separately for children and adults by the type of facility, for example, clinic versus hospital, and we're exploring other dimensions, such as calculating patterns separately for each region in a country. For each of these applications of the algorithm, we estimate values that we expect to see reported by facilities based on global patterns. When a facility reports a set of metrics that is very different from what we expect to see, we flag the facility for root cause analysis. Here's an example output using data from an anonymous set of facilities. The values in each cell are the HIV metrics as reported. The values in parentheses are the values we estimate using recommender systems based on patterns observed across all facilities and indicators, as well as the other values reported for that facility. So looking at the first row for TX-cur, 127 would be the number reported by the facility. 172 would be what we would expect TX-cur to be based on the general patterns observed between TX-cur and other indicators, as well as the 5 other values reported by the facility on that front row. Parentheses color-coded in red are those where the values reported deviate from our expected values. So moving across the top row under TXML and TXRTT, you'll see 2 examples where the number in parentheses is very different than the number reported. Facilities in the top 4 rows all show anomalous data points. Facilities in the bottom 3 rows show values very much in line with expectations. One benefit of this approach is that it works with sparse data. Notice the blank cells in the table. These approaches work well with missing data. This is how Netflix can use the approach to predict not just the movies, not how much you'd like the movies you have seen, but how much you would like movies you haven't seen. So too here. Second, notice that the red cells tell the analyst not only which facility is anomalous, but which indicator or group of indicators is driving the determination that the facility is anomalous. And third, as Tara mentioned, this approach is unsupervised, meaning it does not require any historical data from data quality reviews, no labeled or ground truth data in order to work. It learns patterns from the data as reported and uses what it learns to assess the same data. The bar, therefore, to using these algorithms is comparatively low. A second approach consists of using time series models. These models can be used to generate forecasted future trends, to capture how variables may affect each other over time, or to evaluate impacts of policy interventions, as Lillian will share later on. Here, we're using seasonal and trend decomposition and autoregressive integrated moving average, or ARIMA models, to capture trends in seasonality and HIV indicators at each facility. Once we break down the time series into its underlying components, we generate a set of expectations for the range in which we expect values to be observed, and similarly flag those data points that are far from what we expect. So here you can see an example of outputs from an anonymous health facility reporting TX-new on a quarterly basis. The graph shows different aspects of the same data series. On the top row are the values as reported. They fluctuate between 100 and 500. The point on the far right, the most recent quarter, is in red. That's flagged as an anomalous data point. The other rows show the components of seasonal and trend decomposition. The second row shows the seasonality identified in the data. Tx new tends to increase over the course of the calendar year, with lower values in Q1, increasing with higher values in Q4. The third row shows the trend in the data. It's an upward trend, though not a linearly upward trend, and not upward in every period. It increased in the early years, it dropped in 2017, and then resumed its increase in 2018. Combining the seasonal and the trend components in rows 2 and 3, we then get an estimate of what we expect Tx new values to be. Comparing these expectations to what we observe in the top row, we get the remainders display in the bottom row. These are the differences between what facilities reported and what we expect given seasonality and trends. The point on the far right shows a remainder of close to minus 200. The observed value going back to the top row was around 200. This big gap, and given seasonality and trends, we expected it to be closer to 400. So the big gap between what was reported of 200 and what we expected closer to 400 leads to our determination that this point is anomalous and requires further scrutiny. As you can see, remainders in the bottom row are seldom zero, but using statistical techniques, we can identify which remainders are so large as to be beyond the range of expected values. So under Datify, we've developed much of the code for this work and are currently testing it on routine HIV metrics across a number of countries, together with analysts from the Office of HIV/AIDS and from country mission offices. We're optimistic this approach will identify data issues in an accelerated and automated manner, enabling analysts to focus their time on investigating the underlying issues. Next, we'll hear from Lillian Magetto, Palladium's Chief of Party for the Tupima County project in Kenya. Thank you.
Thank you very much, Yoni, and I'm glad to have the chance to speak with you today. In this presentation, we're going to discuss a method called a controlled interrupted time series, which is a quasi-experimental approach to evaluate the impact of policy interventions using data collected over time, and an application of this method to evaluate the impact of indoor residual spraying, or IRS as I'll refer to it, to combat malaria in the Lake Victoria region. Next slide. Tupima County project is a 5-year USAID funded project that supports measurement, learning, and accountability system strengthening at county level. The project provides technical assistance to 4 health programs. And in particular today, we are going to discuss the support that Tupima County provides to the malaria control program, specifically around strengthening its data quality interventions and analytics in
Hi folks, just 1 minute, we'll try to get Lillian back.
county. IRS was not reintroduced. And at the end of the day, one of the key questions we'd like to answer is, what impact has IRS had on malaria positivity in the region? Thus, the malaria positivity analysis by TK. Next slide. The ideal way really to measure the impact of a policy intervention, as earlier mentioned by my colleague Yoni, is by a randomized controlled trial in which subjects are randomly assigned to treatment and control groups to control for confounding variables. Differences in outcomes between these groups can be associated with the treatment itself, but in many situations, randomized control trials are not used due to various reasons. Probably they are not practical, they may not be ethical, and so on. In the absence of randomized control trials, then ITS or interrupted time series is then used, a version of regression that is suitable for time series data. The idea is to capture trends in a metric of interest separately before and after an intervention and to compare the trends. Also required is a hypothesis of what the impact a policy might have, and for our case is reintroduction of IRS. Will it cause an immediate drop in the number of malaria positive cases? We will see that as we go through our presentation. The metric of interest, as we shall see, is malaria positivity, while the policy intervention is IRS in certain locations, as displayed by the graph you can see on the right-hand side. One way to do this is to use regression analysis with dummy variables to represent a period in which an intervention is in place, or the duration since a policy intervention was introduced as an approach, also known as segmented regression. With time series data, this approach is not always valid. And because regression analysis requires that predictors are uncorrelated, which is not often the case with time series data. And it is not the case here. For example, the number of positive tests in March of a given year is correlated with the number of positive tests in February and with March of the previous year. Instead, then we are using a version of regression analysis which is better suited for time series data, also known as autoregressive integrated moving average, or in short known as ARMA, which accounts for factors such as seasonality and the correlation between malaria positivity in the consecutive months, really when mosquito breeding patterns post the rainy season. We are going to look at Migori County, and we begin by plotting the number of positive cases, the number of positive malaria tests in Migori County over time. And we would like just to mention that IRS was reintroduced in Migori County in February and March 2017. So we begin by training the ARMA model on the 5 years of data to capture seasonality and correlations in the data. Our hypothesis, as I mentioned earlier, is the reintroduction of IRS will cause an immediate drop in the number of positives. So then we went ahead to include step dummy variable. And looking at the resulting parameters of the ARMA model, the estimate of the immediate effect of the introduction of IRS was actually a drop of approximately 17,000 positive tests per month. Next slide. To further evaluate the impact, we are using ARMA model to forecast the number of positives per month, and we'll begin by looking at from April 2018, as though the pattern continued without the interruption, without the introduction of spraying. Next slide. I would like us to look at the charts. Oh, sorry, previous slide. Where the red line represents our point of focus and the gray shaded area represents a 95% forecast interval, meaning that the shaded area, the difference between the red and the blue represents the model's point of estimate of the number of positives prevented by malarial spraying. Clearly, this gap is showing that there's substantial difference between the forecasted counterfactual and the much lower blue line representing the actual number of positives recorded. Next slide. In Homa Bay, our second county of interest, IRS was reintroduced a year later than in Migori, that is in early 2018. And we followed the same approach where the results we can see are consistent with what we found out in Migori. The estimated magnitude of drop in positivity associated with the introduction of spraying was about 18,000 positive cases. And this is when we compare, you can see the red line and the blue line. That difference there, that gap is what we are saying there is substantial drop in the malaria positive cases. Similarly, the actual, comparing the counterfactual against the actual number of positives tested for Homa Bay, we can see that the forecast in red is well above the actuals in blue, although the blue line is generally within the lower bound of the 95% forecast interval. Here, the forecast interval is a little wider than for Migori, suggesting that the model actually will have benefited, in this case, from additional data points to better capture the underlying temporal components. Next slide. And this is because one of the limitations with interrupted time series as compared to randomized controlled trials is the inability to account for confounding variables. Although Migori and Homa Bay show declines in positivity associated with the introduction of IRS, in theory, there could be other malaria control interventions and or policies that occurred simultaneously that actually caused the drop in positivity. And for this case, we can allude to use of the long-lasting treated nets, improved case management, and so on. With the benefit of data then now from the 6 other counties in which IRS was not reintroduced, we've extended our interrupted time series analysis to what is called a controlled interrupted time series, or a quasi-controlled group, where we seek to identify changes in positivity at the same points in time in which we observed changes both in Homa Bay and Migori. This allows us, or has allowed us, to try and control for confounding factors or variables that may have affected actually malaria positivity across the 8 counties. There could be weather events, there could be changes in policy or other interventions. When we look at Siaya County, which is one of the 6 other counties where indoor residual spraying was not done, we did extend our ARMA analysis using the 2018 reintroduction of spraying in Homa Bay as our point of comparison. And looking at the graph on the right, you can see that there is no change observed beginning in April 2018. The actuals in blue, you can see that, fluctuate around the forecast in red. The results in Siaya is suggesting that the change that occurred in Homa Bay in 2018 and in Migori in 2017 that led to a reduction in malaria positivity was in fact the introduction of spray, and not another factor that will have affected all other 8 counties. Then what are we saying? Policymakers know that IRS is an important intervention to eradicate malaria in Kenya. And in April of this year, there was a high-level meeting
Hi, folks. We'll wait for Lillian to return. I think as Lillian was about to say, and when she gets back on, I'll hand back over to her. But there was a meeting a few months ago of decision makers in the Lake Victoria region where they expressed their commitments to support malaria eradication in their counties, including funding interventions that have worked, such as vaccines, indoor residual spraying, and environmental manipulation.
As to quantify the value.
Thanks, Lillian.
Oh, apologies. You had lost me, sorry. So in conclusion, I'm saying that the previous analysis together with the other ongoing analysis will help policymakers quantify the value generated and determine whether to continue and extend spraying to other counties. And this is a point in case that this analysis is really pertinent as we advance malaria elimination in countries. Thank you, and over to you, Yoni, for Q&A session.
Thank you, Lillian, and thank you, Laureen. Palladium is proud to have worked on this diverse set of projects using these methods to find solutions to important health problems. We also appreciate the support of USAID, the CDC, and the President's Malaria Initiative in Kenya for their support for the work discussed today. Now, we'll look forward to questions that you'd like to pose. I think Georgie posted instructions in the chat box, so please paste your questions in the chat box. I think we have a couple that have already come in. So starting out, Laureen, and maybe I'll ask Laureen and Lillian if, Lillian, if the connectivity is not great, but Laureen, if you want to turn on your camera for the Q&A. So Laureen, one question we have is, what are the types of features used in the models that you described? And features is just another word for variables. What are the variables, the inputs? Maybe separately for what did you take from the National Data Warehouse aligned with the screening questions, and what are some of the geospatial or locational variables that you pulled in?
Yeah, so thank you. So what we used is what is collected for HIV testing. That is just a few examples. Examples are like the age of the client, the marital status, gender, whether they've been screened for TB or not, if they have been tested for HIV, or if they have conducted a self-HIV test in the past few months. So those are some of the variables we used. And then, of course, we also got the final test results. We used that also just to train the model. And then for the extra variables that we used was about population, like maternal health, and just the data from Facebook for Good, just to use for the facility, like three kilometers around the facility. So those are some of the variables we used.
Thanks, Laureen. A question for Lillian. Lillian, in the interrupted time series analysis, why did you use the number of positives? So you were looking at the number of positives over time rather than the positivity rate over time. So the hypothesis being that the reintroduction of spraying would reduce the number of positive tests, not necessarily, or not focused on the positivity rate. Can you, Lillian, do you have any thoughts on that?
Right. We used number of positive cases unlike positivity rate because one, we know that not all the regions or sub-counties within for example, one of the counties that indoor residual spraying was happening. And we know that because we really wanted to present or bring out if there would be a drop in the cases that are tested over time with the introduction of this policy intervention or with this intervention for malaria control. We are cognizant that yes, we should have used the malaria positivity rate or incidence rate, but yes, we just said we wanted to see the drop in terms of cases. Over to you, Johnny.
Thanks, Lillian. Right, so the positivity rates would be affected not only by, would have a denominator that could potentially change the story. So we may, it could potentially, I could imagine a situation in which the number of people getting tested may fluctuate in response to some stimulus, and that might obscure the results. Let's see, a question back to Lorene. With respect to the HTS predictive model, how did you handle covariance between the predictor variables? So there were two variables that were correlated. Sorry.
I would request if Yoni can handle that.
Sure, yeah, right. So, well, with the types of algorithms that you described, so with the logistic regression, covariance has to be addressed. Because like with Lillian's example with the regression analysis, there are certain assumptions behind the independence of the predictor variables. For the other models, the tree-based models, the random forest, the XGBoost, the artificial neural networks, there's not a covariance between the indicators is not problematic. There's no assumption of independence of the regressors for those models. So essentially, for logistic regression, we did have to look at the covariance and remove collinear variables. For the other families of supervised models, there was no need to remove collinear variables. Not that we saw very strongly collinear variables. Let's see. Sorry. Here's a question that just came in from the presenter's experience. What are the top 3 pitfalls to predictive modeling? And it's an interesting question. Lorene or Lillian, I think you might have different perspectives. Do you each want to take a pass at it? Lillian, maybe we could start with you. Pitfalls to predictive modeling. Lillian, can you hear me? Lorene, do you want to take a pass?
Yeah, so I think from our scenario, we got a few variables that we used, and the people in the field were not able to explain how it's related. The clients who were tested on Monday as a day we had more clients who tested positive on Monday than other days, or a specific month than a different month. So we still the epidemiologists are not able to put two and two together, how does that affect modeling? If you're tested on Monday, how does it affect? So I think that is one of the things we realized.
Thank you, Yoni. I think I can also maybe give a shot on pitfalls around predictive analysis. That one, regression analysis does not, it's easy to understand, but cannot capture complex relationships. And for this case, you could see that we try to use weather data, various other data sets. And that is one of, can I call it pitfall, that ruins predictive analysis of what basically we were using. And being cautious to make correct assumptions on the underlying training data, such as the correlation we were having that due to a rainy season, say seasonality of variations, that preceding months have right.
I think Lillian may have cut out again. I may just add, and I think it's related to what Lillian was. Sorry, Lillian, please go ahead.
Right, I was saying that making correct assumptions on the underlying training data is one of the other pitfalls. And of course, when it comes to not investing time, when it comes to decision making and based on data and the predictive modeling, it really needs a lot of time for us to be able to do this. And hence the period, say 5 years, trying to predict how the malaria positive cases will look like over time, month by month. Thank you, and over to you, Yoni. You can add.
Thanks, Lynn. Yeah, maybe one thing I would add, and more of a process and stakeholder comment than a technical comment. So I completely agree with everything Lorene and Lillian just said, but I think one of the, in my experience, one of the pitfalls to predictive modeling projects or data science projects is too much of a separation between data science teams and program managers, folks who are actually going to be the end users of whatever the model outputs, whether it's prediction or analysis. I think it tends to struggle when a data science team takes a project, goes off for a few months, and then comes back to the end users and says, "Here are the results." I think these projects tend to work much better when it's a collaboration, because even stakeholders may not, who are not steeped in machine learning, they may not understand all the intricacies of the models, but they tend to understand the data and the domain. And that's important, not only because they can guide the data science teams, but also because they can provide their own validation of the inputs and the process and the outputs. That domain knowledge and knowledge of the data is critical for getting the inputs and the process right for the data science team. And of course, making sure that the actual application is useful and usable by the end user. That requires constant collaboration, and that process is critical. There can't be a division between the data science team, the modeling team, and the actual groups that know the domain and are going to use the outputs of whatever the data science team produces. I see a couple more questions, maybe a couple can try to knock out a little bit quickly. Do you have any data on the feature importance from the trees? This is going back to Lorene's presentation. Lorene, I think not in this presentation, but do you want to say a little bit about the analysis on to understand what is driving the modeling predictions, what variables and how you looked at that? Lorene, can you hear me? Okay, so if Lorene can chime in, I think since we collaborated on that work, we use a couple different approaches to look at variable importance. One is an algorithm called Garuda, which essentially runs a version of the random forest model hundreds of times, and each iteration of the model, it captures to what extent the model used different variables to make its predictions. That gives a global model level picture of what are the variables that are most important in for the model in making its determinations. We also wanted to understand better at the patient level, what information is the model using every time it makes a prediction in order to make that prediction either more in the positive direction or towards a negative direction. For that, we're using something called line analysis, which can be used both to describe models at a global level as well as to create a patient level approximation of the complex model to understand for this patient level what are the variables and values driving it. So those are some of the approaches that we're using to try to understand more about not just how accurately the model makes predictions, but what about each individual patient is the model using to make the prediction that it makes. I think we have time for a couple more questions. I see a question on OLS for malaria. So OLS that's part of what I think Lillian was speaking to, and that the assumptions for OLS don't hold here because of the non-independence of the input variables. A question for Lorene, if you're back on. Do you think using data from Homa Bay County alone for piloting the HTS model was a limitation. I imagine some factors, structural, social, behavioral, economic, and home bay, may not be generalizable across the country. So Lorene, do you want? I believe the models were generated separately using county-specific and facility-specific locational data. Do you want to speak to that?
Yeah. As Yonia said, the initial data set that we had was like 1.9 million records. That was for all the counties that we are in. So what after like running the models in the entire data set, we realized that different counties have different, they're performing differently. So we decided to generate per county. That way we are looking at facility, we're talking about 3-kilometer radius, the population around the facility. So we have different models. So we already have a Siaya model, Nairobi County, Homa Bay County, Machakos. So we have different because of the different population and socio-economic per county.
Thanks, Lorene. I see a question on around the recommender systems and data review presentation. Maybe just to clarify the output. So the question was, I was referring to anonymous facilities, but the data seemed to be individual level. The data was actually, it was facility level, disaggregated by sex and age. So that it was not patient level. It was at all the analysis that we're doing is using aggregate data, but the most granular level of the aggregate data is the facility disaggregated by sex and age. So yes, this approach works right with Netflix and with Amazon. It's often individual level models, but we are using it only on facility level aggregate units. Maybe time for one more question. So given the presentations, given the discussion on data quality, I'm wondering if there was any data cleaning or other data quality improvement efforts needed for the malaria analysis. So Lillian, do you want to speak to data quality issues among the data used for the analysis, maybe also among the patient level data that's supporting other analyses?
Thank you, Yoni. And quickly, I would like to mention that yes, a lot of data quality was done, checks were done, remembering that especially in the sub-counties where we are also implementing another study known as ScanForm study, using ScanForm where we really want to improve quality of data. So that is the same data that has been input into KHRS for us to be able to use the aggregate data. Yes, data quality checks were done, and we can confirm that that is not an issue at the end of as we use the data for the analysis. Thank you.
Thank you, Lillian. Looking at the time, I think I'm going to hand back over to Tara for closing remarks. Thank you, Lillian and Lorene, for your answers.
Great. Thank you, Yoni. We are at the end of the session today. I just want to take a minute to thank our panelists for all the hard work and preparing the presentations for today, of course. Excellent job, everybody. And also, particularly, I'd like to point out Yoni, whom I seem to somehow have not introduced at the beginning. Yoni is our principal data scientist here at Palladium and really responsible for a lot of our sort of accomplishments in this area. So thank you, Yoni, very much. The presenters, thank you. And lastly, I'd like to thank all of you who have attended today and for particularly for your patience with one of the joys of webinars, our internet connectivity issues. So your questions were extremely thoughtful and spot on and really interesting. So thanks to everybody, and we had a great time today, and stay tuned. There will be a recording of this presentation that will be made available. So thanks again, and have a great day, everybody. Bye-bye.